So we are on to the last section in this chapter, and section 11.3, which is titled Taylor series, which we'll write as TS. So first let's remind ourselves of the following. So we have been studying power series and we were given some power series. So someone gave us a power series, and suppose this is a power series that we had. So what did we do with it? So all we could do was study the convergence of this series. We could not find what function it converged to. So when you have this power series, we found that it converges on some interval. So that means it comes to something. It 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 adds up and it sums up to something. Now it obviously will add up to something which is going to be a function of x because it's got x in it. But the thing is that we never knew what is this function. So we could not find what function it converged to. In fact, we never know where this series came from. So most of the time when we were studying series, all sorts of uh, convergence we could study, but we never knew what they were equal to, except for two power series. One was this, and as you would remember, this one turns out to be equal to 1 over 1 minus x. Equal means it sums up and converges to this, and this one was 1 over 1 plus x. But we did not know what function a given power series converged to. So again, quickly reminding you, 11.1 we saw Taylor polynomial. Please start making a distinction between Taylor polynomial and Taylor series. So now this section is on series. Okay, so 11.1 was mostly on Taylor polynomial, which was to approximate a function. Then on the next section we studied power series, which was something given to us something like this, and all that we did was we studied the convergence. But as I explained all along, so when it converges a power series, it converges to a function of x. And what is this function is something we didn't worry about. So now in this section we'll see the source of these power series. Where did these power series come from? And so that is the idea. So we know that a function can be approximated by a Taylor's polynomial. We also know from the remainder theorem of the first section that this approximation improves as n goes to infinity. So as you take more and more terms in the Taylor's polynomial, it becomes more and more accurate. So if we find the Taylor polynomial, which we know very well how to do, and then increase n to infinity, what we get is a power series. Obviously it's a power series, and we turn around and call it a Taylor series. So first thing to notice is Taylor series that we are going to study is a power series. It is a power series. We just call it a Taylor series because it comes from Taylor polynomial. So just to have the name Taylor, we call it Taylor series. There's nothing special about Taylor series. It's just a power series which is derived from Taylor's polynomial. And this Taylor series, again repeating, which is just a power series, will be equal to the function that generates it. So the idea is that, remember, f of x could be approximated by a Taylor's polynomial. So we wrote it as Pn of x. Then we studied that it becomes equal if I take the Taylor's polynomial and add the remainder to it. This was that remainder, the error. So now as n goes to infinity, remainder goes to 0, which was the remainder theorem. So f of x becomes p as n goes to infinity. So I'm making up this notation, p infinity x. That means basically the Taylor series. So once you have this idea as to what we are doing, we can read this box and it puts it all together. So a Taylor or a Maclaurin series for a function. So we are given a function f. It has all the derivatives on an interval which is centered at a, same old ideas. And then the Taylor series for f centered at a is given by this. The main thing to notice is that this is an infinite series, so you keep adding on and you get this in a compact form. Again, notice that it's a summation to infinity. If you had stopped at n, it would have become Taylor polynomial. A Taylor series centered at 0 is called Maclaurin series. So in honor of Maclaurin, who also found this result. So steps in finding a Taylor series. So pretty obvious. First we are going to find the Taylor polynomial for some suitable value of n. So we'll take some n like 3 or 5 or 7 or 6, whatever. Then extend the polynomial to become a series. So that means you just extend it to infinity. Then you have to observe the pattern to write it as a series. So this I'll explain when we do examples, what I'm trying to say here, because we have to write it as a series in this manner, starting from k, from 0 to infinity something. And then the third step is to find the interval of convergence of this series. Now I'll do an example or two, but at this time we generally skip step 3. That means we are not overly interested in finding the interval of convergence. We are more interested in finding the series itself. So although we have learned how to do this in the previous section, the previous section was finding interval of convergence. So once we have a Taylor series, we can always find the interval of convergence, and that's what we studied in section 11.2. Okay, so actually there's going to be almost nothing new here except for how to observe the pattern. So let's find a Taylor series centered at 0, which means basically we're going to find Maclaurin series for e raised to the power x. So again, quickly remind you, to be able to write this, all I need are the f of a, f prime, f double prime, f third prime, and so on. So my function is e raised to the power x, and I have to find it at x equals a, which is 0. So this is going to be 1, e raised to the power 0. F prime at 0, sorry, f prime at x is this. So at 0 also it is 1. Second derivative is also this, so that's also 1. So all these guys are same in this case. So let's write the Taylor polynomial first. Okay, so suppose I'm going to write it till P3. So what would I have? F of A is what? 1 plus F prime at A, which is also 1, times x minus 0 plus 1 over square factorial 2 times x minus 0 squared plus 1 over 3 factorial x minus 0 cube. So this is basically saying this. So this is step 1. This is this step 1. So I have done step 1. Step 2 says now extend the polynomial to become the series. So that means now you can write f of x is equal to, instead of writing P3, which was the polynomial and an approximation, now you can claim that it is the function itself, and that would be this, and then you say plus and write 3 dots. So this was a polynomial and this is the series. Very simple to make it into a series. For free you can put 3 dots, but that does not get you the credit of the question or any other result, because here is the main thing. This is the main thing, so please pay attention. How do I write it as a series? In this case it's pretty obvious. I would say summation. Now notice you have x, x squared, x cubed, so they are all going xk, x raised to the k, and they are divided. Square is divided by 2 factorial, x cube is divided by 3 factorial, so it's divided by k factorial. And my k starts from, notice that the first term is 1, that means x raised to the power 0, so therefore it starts from 0 and goes on till infinity. So this is the Taylor series, and this is the answer. This is not the answer. So let me repeat again, you have to write it as a series. Taylor series is a power series, so you have to write it in a series structure. Step 3, find interval of convergence. Now as I've said, most of the times you'll skip this portion, but let's do it for this one. So how do you find interval of convergence? We remember we are going to do the ratio test. So first thing is I'm going to do ak plus 1 over ak. So that's going to give me x to the power k plus 1 over k plus 1 factorial divided by ak is going to give me this. Simple algebra gives you x over k plus 1. Now as usual you're going to break it up into two things. One is the x component and the other is the k component of it. Now we are ready to take k going to infinity. So now notice, as k goes to infinity, this goes to 0 for any x, whatever the value of x is. So for any x, because k is in the denominator. So that means this is the limit is 0 and which is less than 1, what we want for any x. So if it's true for any x, that means my interval of convergence is negative infinity to infinity. So this is my interval of convergence. So very powerful result. That means f of x can be written as this power series, what we just found, for all x, not just near 0. This converges for all x, which is quite interesting. Okay, let's continue on to the next example, where the function is sine x, and this one is also about a equals 0. So as before, we are going to take the function and then we're going to find it at x equals a, which is 0. So the function is sine x. So f of 0 is sine of 0, which is 0. Then f prime of x, so the derivative is cosine x. So f prime of 0 is cosine of 0, which is 1. So f double prime of x is going to be negative sine x. So f double prime at 0 would be 0. The third derivative is going to be negative cosine x. So the third derivative at 0 would be negative cosine 0. So that's negative 1. The fourth derivative would be plus sine x. So at 0 that would be 0. Let's go one more. Fifth derivative would be cosine x. So the fifth derivative at 0 would be 1. So notice there's a pattern here, the 0 1 0 negative 1 0 1. So this continues in this manner. So now we have to set up the Maclaurin series. So the step 1 is the Maclaurin polynomial. So let's first write it as a polynomial. So I'm going to get f of 0, which is 0, plus f prime at 0, which is 1, times x. So that is the x. Then plus f double prime at 0, so that is 0. Then f triple prime, and that is negative 1. So negative 1 over 3 factorial times x cube, plus the fourth one, which is 0. Then the fifth one, which is 1 over 5 factorial x to the power 5, and so on. No, it's a polynomial, so I'm stopping here. So let's first write it and see what we see. Minus x cube over 3 factorial plus x5 over 5 factorial. So this is my polynomial. The second step is, now we are ready to write it as a series. So now I could say the function, which is sine x, is equal to x minus x cube over 3 factorial plus x5 over 5 factorial, and you can extend it, minus x7 over 7 factorial, and so on. So we put these three periods, three dots. Now comes the main thing, and that is to be able to write it as series. So few things to notice. First thing is that it's an alternating series. So it's plus, minus, plus, minus. So clearly I have to have -1 raised to the power k. Now remember, our k is starting from 0. So when a k is 0, I get a +1. So that's what I want. Then when k is 1, I want -1, and that's what I get. So that's fine. So in -1 to the power k. Then x raised to the power odd powers. So it's 1, 3, 5, 7. So that means 2k plus 1. You should always check when k is 0, I'm going to get 2 times 0 plus 1, so I'll just have x. And then when k is 1, I'll get 2 times 1 plus 1, which is 3, so that's correct. Okay, and divided by, now notice when you have cube, you divide by 3 factorial, 5 factorial. So that means 2k plus 1 factorial. So this is the Maclaurin series, Taylor series, or Maclaurin series of sine x. So that means sine x is equal to this. Now for what values of x that this works? So that is supposed to be our third step, that we are supposed to find the interval of convergence, so that we know that this holds, this convergence, this equality holds for what values of x. So again, as I've said before, we are not really involved in that in this particular course, but you could always do the ratio test and find it. We have done this, so let me do it for this time. -1 to the power k plus 1. This is ak plus 1 over ak. So then x raised to the power 2 times k plus 1 over 2 times k plus 1 plus 1 factorial, and then you have 2k plus 1 factorial over x to the power 2k plus 1. Now this is going to go away because I have an absolute value, and then here I have 2k plus 2 plus 1, so that is 2k plus 3, and here I have 2k plus 1, so I'll be left with x squared. Now let's look at the factorial. So I have 2k plus 2 plus 1, so that's 2k plus 3. So in the denominator I'm going to have 2k plus 3 times 2k plus 2 times 2k plus 1 factorial. So this is the recursion of 2k plus 3 factorial. So I've gone down one step down till here, because in the numerator I have this, so this cancels with this. So I'm left with absolute value of x squared divided times 1 over 2k plus 3 times 2k plus 2. Now we are ready to take k going to infinity. Now clearly, with k in the denominator, this is going to go to 0 for all x. In other words, it doesn't matter what this x is. When k goes to infinity, this is going to force it to go to 0, whatever x is. So therefore my interval of convergence is minus infinity to infinity. So that's great. That means this series works for all values of x. Okay, let's continue with the final practice example. So the function is log of 1 plus x and the centered at a equals 0. So again, let's start with our function and then find the values at x equals a equals 0. So what is f of 0? That is ln of 1, which is 0. Then the derivative is 1 over 1 plus x, which I could write it as 1 plus x raised to the power minus 1. So f prime at 0 would be 1. Put x as 0 here. Let's go for the second derivative. So I'll get minus 1 times 1 plus x raised to the power negative 2. And the chain rule is going to give me a 1, which is okay. So my f double prime at 0 is going to be negative 1. Let's find the third derivative. So that will be negative 2 comes in front, so it becomes 2, 1 plus x raised to the power negative 3. So f double prime at 0 is 2. Let's do one more. The fourth derivative would be minus 6 times 1 plus x to the power negative 4. So the fourth derivative at 0 is negative 6. So let's set up the Maclaurin's polynomial. So what is it? P4 of x. So that is what f, just to remind you, although we know it very well, f of 0 plus f prime at 0 times x plus f double prime at 0 times x squared plus, and for till the fourth power. So let's go. 0, f of 0 is 0 plus f prime of 0 is 1 times x, then minus 1, second derivative is negative 1. Oh, this has 2 factorial here, divided by 2 factorial times x squared. Then the third derivative is plus 2 over 3 factorial x cube, and then the fourth one would be minus 6 over 4 factorial x to the power 4. Okay, so let's clean it up. I get x minus x squared over 2 plus, now 2 is in the numerator here and 3 factorial is here, so 3 factorial is 6, so 2 and 6 can cancel and leave me with a 3, so I have x cube over 3. Now 4 factorial is 24, and then I have a 6 here in the numerator, so I get minus x to the power 4 over 4, because 6 and 24 leaves me with a 4. So this is the polynomial. So the second step is to write the series. So the Maclaurin series f of x would be equal to x minus x squared over 2 plus x cube over 3 minus x4 over 4 plus and 3 dots. And now I have to write it as a power series. So let's see. So first thing to notice is that it's alternating series. I have a plus, a minus, a plus, a minus, so that means a negative 1 to the power k should do the job. K is starting from 0. Now the first term is x, the second one is x squared. So x raised to the power k is not going to do it. I need k plus 1, because when k is 0, I want it to be x. So that means I need k plus 1. Now the denominator is, if this is square, it's 2, it's cube, it's 3. So the denominator is same as the exponent. So therefore, this is the power series, Taylor series, Maclaurin series for log of 1 plus x.